Hi everyone. So today we will be discussing how to solve bubble and dew point calculations for vapor-liquid equilibrium mixtures. So the first example we have is for a binary mixture of acetonitrile and nitromethane, and we want to prepare a graph showing pressure versus composition at a temperature of 75 degrees Celsius. So in the absence of any additional information, we're going to assume that this system behaves ideally, so we're going to use Raoult's law. So which states that the total pressure of a system is equal to the sum of the partial pressure of all the components in the system times their mole fraction. Okay, so obviously to do this, we need to first find the partial pressure of the components in our system. So we can achieve this by finding Antoine equations for acetonitrile and nitromethane. So I'm going to, okay, so now that we have the correlations, we can calculate the saturated vapor pressure of both components. So the first one is equal to 83.21 kPa. The second one is equal to 41.98 kPa. So from the Raoult's law, we know that the total pressure needs to be equal to P1 x1 plus P2 x2. So we can rewrite this expression in terms of a single component by remembering the fact that x1 and x2 is equal to 1. So this means that P can also be written as P2 plus P1 minus P2 times x1. And if you do the algebra, you'll see that this works out. So now what we do is that we set an arbitrary value for x1. So let's say x1 is equal to 0.6. And let's calculate P. So it turns out that when we do this calculation, P is equal to 66.72 kPa. So now that we have the pressure, we know that for each specific value of x1, there's going to be a corresponding value of y1. So for every value, every liquid composition, there is a corresponding equilibrium vapor composition that the system has to have. And so in this case, we can find it by applying Dalton's law. So y1p is equal to x1 p1 p1. So rearranging, we write this as y equals x1 p1 divided by p, and this gives us 0.7483. You basically repeat this calculation for different values of x1. So you can choose intervals of 0.2, for example. So you can choose x1 is equal to 0.2, 0.4, 0.6, 0.8. And then after that, you find the corresponding values of y1. And this will give you enough points to draw your graph. When you finish calculating your x1 and y1 values, note that for each corresponding pair of values, you get a different pressure because your composition is different. You should get these values if you go with intervals of 0.2. And when you plot this on the graph, you'll get something like this. So x1 is the line on top, and y1 is the line on the bottom. And of course, this is with respect to pressure. You could also do this graph with temperature instead of pressure, and it would be very similar. So what are we looking at exactly? So this is your binary phase diagram. And so on the top is your subcooled liquid region. So this is liquid. And on the bottom is vapor. So down here is superheated vapor. And in between, so in this envelope here is you have two phases coexisting. So this is your two-phase region. What this means is that if the composition of your mixture falls inside this envelope at a given pressure, then you will effectively have two phases. So this means that if, for example, if you were to have a mixture composition of 0.5, so right here, so your pressure, as your pressure increases, so eventually you'll start to see liquids start to form in your two-phase region. And then the composition of your liquid and your vapor can be determined by just finding the phase lines that correspond to your pressure. So let's say your system is at this pressure. This means that here your liquid composition would be this, and your vapor composition would be this. And eventually, as you increase your pressure, eventually your whole system condenses and becomes a full subcooled liquid in this region. A few things to note here is that this point here is just the vapor pressure of your pure component. So this is P2, and up here is your vapor pressure of your pure first component, so P1. And so if you draw a temperature diagram, this is almost exactly the same. The only difference is that your vapor phase is on top and your liquid phase is on the bottom. So that concludes how to draw binary phase diagrams. And if we want to do the same thing but with a set pressure instead of a set temperature, then it's very, very similar, except that for the Antoine equation, you will need to rearrange it so that you solve for temperature instead. So it will look something like this. And basically you plug in all your parameters and you get T, and then after that the problem solution is almost identical. So you'll need to solve for X via the equation, and then after that the rest of the solution is identical.